In this video we're gonna continue working with limits. Only this time the only thing we're gonna do is prove some theorems and propositions that will make our lives easier when solving the exercises. And this is the first theorem. If we have two sequences, a sub n and b sub n, each with limits L1 and L2, then the limit of the sum of the sequences is equal to the sum of the limits. Let's see if we can prove this. Our hypotheses are that the limits are L1 and L2. So we have to start using the definition of the limit. If you don't remember this definition, then I recommend you go check out the last video when we worked with some examples using this definition. So let epsilon be a number greater than 0. And what we're gonna do is we will take epsilon over 2 in the definition of the limits a sub n that tends to L1 and b sub n with limits L2. What I mean by this is that when we take epsilon over 2, then there exists a number n1 such that if n is greater to this number n1, then a sub n minus L1 is smaller to epsilon. This is the definition of the limit of a sub n. And then the same, taking this epsilon over 2, there will exist a number n2 for which if n is greater than n2, then b sub n minus L2 will be smaller to epsilon. And, this was epsilon over 2 in both cases. And this is the definition of the limit for b sub n. So now, if we let n, a number, be the maximum between n1 and n2, so that is, we take the maximum between these two numbers, then whenever we take a number n greater to n, this number n will be greater to n1 and to n2. And so these two things will be true. Then two things will happen. A sub n minus L1 is smaller to epsilon over 2, and also b sub n minus L2 will be smaller to epsilon over 2. Now what we want to prove is that the limit of a sub n plus b sub n equals to L1 plus L2. And the definition of a limit tells us that for every epsilon greater than 0, there exists a number n for which what we have to do is subtract the thing we're trying to get the limit minus the limit. And we have to try and make this smaller to some number epsilon. So let's try and do this calculation. In this case, we have the absolute value of a sub n plus b sub n, and we'll subtract the limit L1 plus L2. We can rewrite this as a sub n minus L1 plus b sub n minus L2. And now we can use the triangular inequality and rewrite this as a sub n minus L1 plus the absolute value of b sub n minus L2. And now, if we take a number n that's greater to this number n, the maximum between n1 and n2, then we know a sub n minus L1 is smaller to epsilon over 2. So this one is smaller to epsilon over 2. And then Bn minus L2 is smaller to epsilon over 2. And this equals to epsilon. So then we had an epsilon, and we found a number n, for which if we take n greater to this number n we found, then a sub n plus b sub n minus L1 plus L2 is smaller to epsilon, and that is the definition of a limit. So with this, what we have is that the limit, when n tends towards infinity, of a sub n minus b sub n plus b sub n equals L1 plus L2. And that is exactly what we were trying to prove. Now from this we get a corollary. This corollary works as another definition of a limit. So we know the definition of when a limit of a sub n is equal to L. But with the theorem we just proved, you can see that it's the same as saying that the limit of a sub n minus L is 0. Because here, when we take b sub n equals to L, then obviously the limit of b sub n is L. And then the limit, because of what we just proved, of a sub n minus L will be equal to L minus L, which equals to 0. And the same will obviously happen with the absolute value. Now we're going to be working with a lemma. This lemma says that if we have a sequence with limit 0 and another sequence b sub n that's bounded, then the limit of the product is 0. Let's have a look at the proof. First, we're going to suppose that c is different to 0. If it was 0, if c was 0, then a sub n times b sub n would be 0. Because b sub n, the absolute value, would be smaller than or equal to 0. So the only option for b sub n would be to be 0. And then the product at 0, and so the limit of a sub n times b sub n will obviously be 0. So we can just say, if c was 0, then we take epsilon over c in the definition of the limit of a sub n. So then for epsilon over c, there exists a number n such that if n is greater to n, then the absolute value of a sub n minus 0, which is a sub n, is smaller to epsilon over c. Now we work with the limit a sub n times b sub n. We can write this absolute value as the product of the absolute values. And then if we take n greater to n, here we are under this condition, so a sub n is smaller to epsilon over c. And then this is times b sub n. But we also know that b sub n is smaller or equal to c. So then this will be smaller or equal to epsilon over c times b sub n, so times c. And this equals to epsilon. So then a sub a times b sub n minus 0 is smaller to epsilon. And that is the definition of a limit. So then the limit when n goes towards infinity of a sub n b sub n is 0. Now another important lemma is that the limit of the product of two convergent sequences with limits L1 and L2 is the product of the limits. So let's now work again with this proof. And what we're gonna do is work a bit on this expression, a sub n b sub n minus L1 L2. What we wanna do is prove that this tends towards 0 which equals to saying that this expression is smaller to epsilon for all epsilon greater than 0. Subtract L1 times Bn and then add it again, L1 times B sub n. We can do this because this equals to 0. So now we can take common factor from here, B sub n, and we'd have B sub n times A sub n minus L1, and from here we can take common factor L1, so we'd have plus L1 times B sub n minus L2. So what we have here is B sub n. B sub n has this limit, and we know that any convergent sequence implies that the sequence is bounded. Again, this is something we proved in the previous video. So B sub n is bounded. Now, because of what we saw, the equivalent definition of a limit, A sub n minus L1 has limit 0. Here, L1 is a number, so again, it is bounded. And B sub n minus L2 is the sequence minus its limit, which also tends towards 0. So we have two products, one of a bounded element and of an element that tends towards 0. And with the lemma we just proved, the previous lemma told us that this product had limit 0. And the same would happen with this one. So the sum of two things that goes towards 0 would be the sum of the limits, and that is 0 plus 0 because of the first theorem we saw in this video. And so with all this we get that A sub n times B sub n minus L1 L2 has limit 0, which also means that A sub n B sub n has limit L1 L2, and that is exactly what we were trying to prove. Now we're gonna have two very similar theorems that will be left as an exercise to prove. The proofs are very simple. The first one can be a bit more tricky because you have to prove that 1 over A sub n is bounded, but with this help that I just gave you, you should be able to prove it. Remember that those who follow us on Patreon, they get the solutions to all the given problems in the videos. For example, the proofs for these two theorems. And now we can continue with another topic, and that is monotonic sequences. And we're gonna start with a definition. We say that a sequence is monotonically increasing if A sub n is smaller than or equal to A sub n plus 1. And this should happen for all natural number n. Graphically, what this would mean is if we here have n, and this is n plus 1, let's say that A sub n is here, so then this number is A sub n. So monotonically increasing tells us that A sub n plus 1 can be equal to A sub n, so it could be here, but it also can be greater. So it could be somewhere around this point. It can be underneath A sub n. So then when we look at the plot of a monotonically increasing sequence, we always get something like this. The sequence is always increasing, and then in a similar fashion we get that a sequence is monotonically decreasing if A sub n is greater than or equal to A sub n plus 1. again for all natural numbers n. So when we plot the sequence, again, this is n and here is n plus 1. If this number is a sub n, then a sub n plus 1 can be equal, so it can be here, or it can be smaller, so a sub n plus 1 can be down here. And then in general, when we look at a plot for a monotonically decreasing sequence, it always looks something like this. So the sequence is always decreasing. It can be constant, the same as with the increasing one. It can be constant sometimes, like in this case. But in general, it is decreasing. And now with these two definitions comes a theorem. And this theorem is extremely important. It says that every monotonic and bounded sequence converges. Monotonic is that it's all the time either increasing or decreasing. And then bounded meant that there exists a number c such that our sequence in absolute value is always smaller than or equal to this number. So let's try now and do the proof. The theorem says monotonic. This will work for either monotonically increasing or decreasing sequences. Let's suppose it's increasing. The proof would be exactly the same or very similar if it was monotonically decreasing. Now, let A be a set in which we'll collect all the numbers in our sequence. Because our sequence is bounded, this set is bounded. So, what we can do is take the supremum of this set A. Let's call it L. Now L is the supremum of our set, and using the definition of supremum, we know that for every epsilon greater than 0, there exists number n, for which if n is greater to n, then L minus epsilon is smaller to a sub n and smaller to L. This is only using the definition of supremum. But now this is also the definition of a limit, so then the limit of a sub n has to be L. And then the sequence converges, which is what we were trying to prove. And now to finish with sequences, we're going to have a look at one last definition. We say that a sequence a sub n is Cauchy if for every epsilon greater than 0 there exists a number n natural, for which when we take n and m, two natural numbers greater to n, then a sub n minus a sub m can be as small as possible. And with this definition comes a theorem. The theorem says that every convergence sequence is Cauchy. Let's have a look at the proof. So let's start by taking a sequence a sub n that's convergent. Let's say that a sub n converges to L. Now let's take, like we need for the definition of a sequence, let's take epsilon greater than 0. We know because a sub n tends to L that a sub n minus L will be smaller to epsilon for every natural number n that's greater to some number n we know exists. But let's take, instead of smaller to epsilon, we can do it for epsilon over 2. Now let's take a natural number m that's also greater than or equal to n. And try and do a sub n minus a sub m. We want to see that this is smaller to epsilon, just to see that this sequence is Cauchy. So what we're going to do is rewrite this as a sub n minus L plus L minus a sub m. Now we can use the triangular inequality and write this as a sub n minus L plus L minus a sub m. This is the same as saying a sub n minus L plus the absolute value of a sub m minus L. But now, because this number n is greater to n, we know that a sub n minus L is smaller to epsilon over 2. So then this is smaller to epsilon over 2 plus, and here because we have m greater to n, then also a sub n minus L will be smaller to epsilon over 2. So we can again say that this is plus epsilon over 2. And this equals to epsilon. So then we start with a convergence sequence, and we proved that whenever we took m and then greater to n, then a sub n minus a sub m was smaller to epsilon. And so this sequence is Cauchy.